Tonight is July the 10th, 2023, and I've got a gorgeous instrument here. I love these general radio instruments. I've got a bunch of them. Got this one not too long ago. Let's zoom in on it just a little bit. It's a DC ohm meter, and you may think, well, you know, how exciting can a DC ohm meter be? Well, I won't disagree, but it measures from 1 micro ohm to 1 tera ohm, 10 to the 12th ohms. 1 micro ohm to 1 tera ohm. I don't think you can read this, but I'll hold it up in front of you. It's actually written right there. And wow, I love it. I like to have fun with it. I don't know if I ever actually need accuracy, what this thing will give you. Let's see, what is its accuracy? What do they state it as? It's something like, let's see, what do they claim it is? Whatever they claim it is, you can probably get that out of it. They say it's, oh my goodness, I've got that on a timer. That's how I make things turn themselves off when I forget them. 1 micro ohm, let's see. My goodness, 0.01%. 0.01. And I believe it. Okay. Well, let's start out. It's got 2 types of scales on it. I'll zoom in there so you can actually see what it says there. One of them is, see, one of them is labeled the Wheatstone bridge, and one of them's measured, labeled Kelvin. Well, the Wheatstone is what we generally use, like in a regular ohm meter with 2 leads. But a Kelvin, we also call it a 4-wire lead, has to use clips like this. Let me zoom back out here. Excuse me, wrong way. Clips like this are what they call Kelvin probes, and the left jaw of metal and the right jaw of metal are not the same. See, there are 2 different wires. So one wire goes to one side, one wire goes to the other. Same with the other probe. One wire goes one side, one to the other. Well, what that does is that delivers the voltage right all the way to the device that you're measuring, so that you eliminate the lead resistance. Okay, so we're going to use both. Now, the Kelvin probes are really useful, and I'd say just downright necessary for measuring very, very low resistances. Well, I've got some things right here that I'll show you. Here is, we won't belabor this too much. Here's a 20 amp shunt, 50 millivolt, 20 amp shunt, made by, oh my goodness, who makes these things? A meter manufacturer. Now I can't find it. I hate it when that happens. Anyway, this is good stuff. Good stuff. Okay, well, see, the 10 amp one, which is this one right here. Is that right? Yeah. The 10 amp one at 50 millivolts would be 50 millivolts, 10 amps. So you do R, which is, we want to know the R of this, the resistance of it, the DC resistance, E over I. So it would be 0.05 divided by 10, which would be 0.005. So this thing right here should measure 5 milliohms. 5 milliohms. So we'll put it in Kelvin. You'll be able to see everything I'm doing here. Yeah. We'll plug our meter back in. You can't have all 4 of them hooked up when you're using it in the Wheatstone bridge. That's why they're unplugged right now. And then we got to get some really good bites into this thing. We could hook that thing up like that, and then just around that block, so we got a good bite on it. Okay, lay it down because we don't want to be bouncing it around. And then we get over here. Let's go zoom in here, and I want to be able to see what I'm doing without me getting in the way. What we got to do first is we put this thing up in 0, and we zero it. We zero it by measuring either by turning either the 0 balance and or the sensitivity gain. But we're going to set this thing to 0. We've also, which I've got off the screen right now, we got to set this thing to is set to 100 milliohms. Okay, now what that 100 milliohms says is this right here. So this would be 100 milliohms. So, and these right here would be microohms. Like this would be 100 milliohms, 10 milliohms, 1 milliohm, 100 microohms, 10 microohms, and 1 microohm. Okay? So what we're going to do now is we're going to zero it very tediously and lovingly. Let it sit there for just a second. And then we're going to put it in measure. See if you can see the measure. Yeah, measure. See, it's much too low now. To the left is way too low, to the right's too high. So we say, is it 100 milliohms? No. Am I doing these right? No, I got it in G, I'm sorry. See, it's easy to mess up. G is conductance. We got to put it R. Okay, it's okay. It's okay. It's easy to make these silly mistakes because I've been tinkering with it all now. Let's set it back to 0. G is conductance, which is just a reciprocal of R. And that's how you measure really high values, like this guy right here we're going to measure. This is a 1.09 gigohm resistor. It'll measure it right up to the money. Okay, now we've got it zeroed again. Yep. Okay, now we flip it down. Ohms, 100 milliohms, like I say, 100 milliohms, 10 milliohms, 1 milliohm, etc. So is it 100 milliohms? No, see, that goes way too far to the right, so that's way too high. Is it 10 milliohms? Nope, that's way too high. Is it 1? Well, it didn't measure it really high. 2, 3, 4, 5. Let it settle in. Right there. It's 5 milliohms. This is dead center, 5 milliohms. You can go back and forth. You can say to 0. See, we're off of 0 just ever so slightly. It's very temperature sensitive. It's sensitive to everything. I love it. Dead center. 5 milliohms. Okay? So now we got a, we'll go to a 20 amp shunt. Get it out here. 20 amp shunt would be 2.5 milliohms. So we'll clip it on there. We'll clip it on there good. Let me get back out and show you what I'm doing here. I'm clipping that guy on right there. And I'm laying it down because I don't want to be moving the wires around. You know, I don't want to be holding them while I'm doing something. And then we go back over here. And if you can see, we just got through measuring the 5 milliohm, and if it's to the center, it's to the right of center, then it's much too high. So we'll go back to 0. You got to go back and forth. You got to love this. And then we'll zero it again. Well, it'll actually go right back to 0. I've got it set to normal instead of fast, which seems to be the best way to do it. Put it in measure. It was much too high. There's 4 milliohms. There's 3 milliohms. There's 2 milliohms. See, now you can see that it moved to the left. So it's too low now. So then we take the next digit. So we got 2 milliohms. Now we're in the microohm range. 100, add 100 microohms, 200, 300, 400, 500. See, it's 2 milliohms and 500 microohms, which is 2.5 microohms. Milliohms, excuse me. 2.5 milliohms. Yeah, these are made by Weston. I couldn't think of the name of it. I hate it when my brain goes blank. But, yeah, these little Weston shunts are just great. You use them on 50 millivolt meters, and they're extremely good. And then we won't measure this one, but this is a 300 amp. And if you do R equals E over I on it, you get E, 50 millivolts again. It's written right there on it, 50 millivolts divided by 300. We won't go there because I don't want to belabor this, but it'll do it. Now that we know this thing does milliohms really well and microohms, let's measure something really high, like this guy right here. And I'll show you how you measure it using the conductance scale. That's what you have to use to measure these really high resistors. Now, the first thing we got to do is we're going to go back to the Wheatstone, and then we got to unplug these right here, because otherwise we're short. You know, we're shorting. One side of this is ground and one side is hot. It's the same thing on the other probe. So we got to unground the. We got to move one of the grounds, and now we got to put this thing as high as it'll go. Yep, and then we put it on G. Putting all these things always back down to 0 is the best place to do it. Put it on 0, zero it out, give it a breath of fresh air here to settle down, touch it up just a little bit. Yeah, when I got this thing, it was actually in quite good shape, but the batteries in it, it has 2 banks of D-cell batteries. It has 4 batteries, 4 D-cell batteries, and 4 D-cell batteries. One of them is used for running the amplifier in there, and one is used for, I think, providing the voltage for the probes. Okay, now, let's see if I can do this right. Now we got this thing in 100 nano mhos, because it's an upside down ohm. You know, the ohm is like this. But the mho is just upside down. It's the reciprocal of resistance. So we got to measure the reciprocal, and then we just convert it, and we get the resistance. Okay, so we're going to be able to. This is the 100 nano mho scale. So this is 100, 10, and 1. 0.1, 0.01, 0.001. Okay. Now we're going to hook this guy up to, oh, by the way, this resistor is out of a high voltage probe. It's 1.090 megohms, 2%, plus or minus 2%, 1.090, not quite 1.1 gigohms. Okay. It's zeroed. We got it in G. We got it on 100 nano mhos, and now we're going to measure it. See, it's too low. If we put in the first one, whoa, see, that's way too high. Way too high. So it's not 100, it's not 10, it's not, well, there you go. Well, that's a little bit too much. Just a little bit too much. Because we're in, you gotta really kind of scope in on this. You gotta love this stuff. See, it's a little bit past the center. I don't know if I'm dead center of the meter. Let me move this thing around. I want you to be able to see this. These things are so delicate and accurate. I love them. Let's get up here as close as we reasonably can while it's still focused. Come on now. Come on, camera. Yeah, you can see that. You can see it's to the right. But we're going to go back to 0. Make sure our 0 is 0. You always got to go back and forth, touching it up. Being very, very dedicated to what you're doing. Put that down. See, that's a little bit too high. So we got to put the 1 back down. And then we start with the next one. 7, 8, 9. If you go to X, what X does is it raises this one to 1. That's what it does. So see, that's too high. Because that was the same as putting this on 1. So we got to move that back down. So it's 0.9. That's about as close as we can read it. That's 0 right there. That's 0.9. No, it's actually just a teeny bit more. Maybe there. Let's see. That's 0. That's as close as we can get. 0.91. Then you got to break out your calculator. Zoom the camera back out. And here's how you do the conductance stuff. Turn your calculator on. Okay, it's 0.19, and remember this is in nano, so it's 0.19 E9 change sign, because it's nano, and then you take the reciprocal of it. I hate it when I make stupid mistakes like that. That would be 100, that'd be 10, that'd be 1, that's 0.9. Yeah, 0.91, I'll get it right. 0.91 E9 change sign reciprocal. There it is, I'm sorry. I really did it right this time. And that, you gotta see this. It's telling you that it's 1,098.9 million. So we'd call it 1.099, right? 1.099, and the resistor says it's 1.090. So, and it's plus or minus a 2% resistor. So this is probably pretty darn accurate. Yeah, I want to show you the way you do it. You have to put in the number. It's 0.91, because that's what we're reading off of there. But it's nano. So with this type of calculator, you say E9 change sign. That makes it 10 to the minus 9, and then you take the reciprocal. See, there's that number. 1.099. 1.099, and the resistor says it is, if you can read that, can't get it too close, 1.090 right there, 1.090 megohms. So it works. I love this stuff. Now, of course, the digital stuff is nice and fancy, and if you're making a living at it and you got to have answers, well, that's one thing. But, I dare say a lot of the stuff that we enjoy today, the vintage stuff, from yesteryear, was made on equipment like this. Down to the old HP spectrum analyzers for audio analyzers that go from 5 hertz to 50 kilohertz, etc. And on, in the old Triplet and Simpson volt-ohm meters, you know what I mean? Well, anyway, I love this old general radio stuff. It's so high quality. It has lasted decades. I think a lot of it comes from universities. And I don't know about this one, of course. It's got some kind of serial number on it right here. But I think a lot of it came from higher learning institutions, and some of them are in such good shape that I have that I think they only got to be used when somebody was working on their master's or PhD, and then they got to bring it out and play with it, and then they immediately had to take it back and check it in and serial number it and sign it back in, and then they locked it back up. Well, anyway, that made them last a long time, and I enjoy having some of these beautiful old instruments where they made it to last. Well, anyhow, I just wanted to document this. General Radio 1666 DC resistance bridge that uses either a Wheatstone or a Kelvin. And you can use either, well, depending on if you use Wheatstone, you got to use 2 wires. And if you use a Kelvin, it's the 4-wire system. So, thanks for watching. I hope this helps. Hope you enjoy this old stuff. Take care. Stay safe. Oh, I want to show you something else. This is something I bet not many people have seen. This is a vacuum tube Geiger counter. Yeah. I want to show you this. Vacuum tube Geiger counter. Hear it popping? And look at this. Look at this beautiful old watch. This thing is cool. Glows in the dark. Can you see the hands on it? With a radium. Watch this. I'll open the gamma shield here. Yeah, watch this. over 1,500 counts per minute. And if you put it down here times 10, it'll settle in. That's back in the day when they they painted these dials so they'll glow in the dark with real radium paint. And by the way, this thing runs quite well. It's not wound up right now, but you can wind it up and then it snaps like this. And then you can set the time on it. Push that back in. Click and it actually keeps good time. I just thought you might appreciate that. I think this little vacuum tube voltmeter, it's got 12AX, 12AU7s. Whoops, I keep forgetting what I'm looking at here. Yeah, it's got some 12AU7s and what have you in it, and a 6X4 rectifier unit. It's all vacuum tube. I think it was used in laboratory stuff. Not laboratory, but you know, like teaching, classroom type stuff. And back in it was CD. You see that CD? Civil Defense. That's what they used to call it. I don't know what they call it now. I guess just everybody's on their own. I don't know what happens. Back then, the Civil Defense was going to warn us, so you remember we could go hide under the tables? Well, I guess everybody figured out that wasn't going to get us anywhere. Anyway, thanks again for watching. Yeah, this is my new basement lab down here, where I have a lot of fun. Here's some of the older general radio instruments over here, and my chemistry and stuff and what have you.